Okay, let's go ahead and get started. Thank you so much for taking some time out of your day to attend this webinar today. So I am Matt Cederberg. I'm the CEO of Coreform, and I'm excited to have Carl Merkley, who will be presenting our webinar today. We also have Greg Vernon and Randy Morris from Coreform who will be helping as well. So here is kind of what we'll be doing today. Basically, Carl will be walking us through an advanced meshing tutorial. First, a little bit of housekeeping. If you haven't been on a webinar before, everyone else is muted. Don't worry about that. Feel free to chat with us whenever you'd like to with the chat or with the QA. And this is being recorded. And yeah. Carl, you might want to mute while you're not talking. If hear a little bit of feedback.
Okay.
So Carl Merkley is the Coreform Cubit product manager, and then Randy Morris is the channel manager as well. And Greg Vernon is our director of product management. A little bit about Coreform. We're the fastest growing CAE company on the 2020 Inc. 5000. So there's about 30 of us now. And the origins of Coreform was we're focused on helping you engineer safer products faster through better math. And the main thrust of our company is we're writing a solver called Coreform IGA. This is the first native isogeometric analysis solver for nonlinear structural response. So that was first released last month. So we're still very rapidly developing that with a number of customers. Greg Vernon will be leading a webinar in 2 weeks on February 9th to introduce more about Coreform IGA. So feel free to register for that on our website. We acquired the Cubit software a little over a year ago, and we're turning this into the foundational pre and post processor for Coreform IGA. But we're also continuing to work very closely with Sandia National Labs to enhance Coreform Cubit for advanced meshing for challenging simulations. And so that will be the focus of this webinar today with Carl, as he will be walking us through some functionality in Cubit. So let's introduce Carl, ask one question, and turn the time over to Carl. So Carl Merkley received his doctorate in mechanical engineering from Brigham Young University in 1998. He has nearly 20 years experience developing meshing tools and algorithms. He is amazed whenever he finds out that someone has actually read his dissertation, and his most cited paper was a class project for his master's degree entitled The Comparison of All Hexagonal and Tetrahedral Finite Element Meshes for Elastic and Elastoplastic Analysis. It should come as no surprise that he has spent much of the last 2 decades looking for better ways to create accurate analyses. So now the last thing I'll do before turning the time over to Carl is share a poll. This is always helpful for us to understand who's here and can reflect some of our language to this. So how much experience do you have with Cubit? Have you never used it? Have you tried but not been successful yet? Have you successfully used this on a few projects? Have you successfully used it for many projects? Or is this the critical software that you regularly use? So I'll leave this open for 5 more seconds. Okay, so here is what we've got. So a number of people that have successfully used this on a few projects, Carl, which is probably the sweet spot for what you're talking to today. And hopefully the webinar is valuable for everyone in attendance. So with that, I'll turn the time over to you, Carl.
Okay, great. So do you want to continue to sharing your, you want to just continue sharing your slides from your machine, Matt? You want me to go ahead and take it over?
Yeah, do you want to go ahead and pick that up?
All right, bring those up. Okay.
And Matt, do you want to, there's a Q&A that people are able to ask questions if they have them. Do you want to go over some of any of those rules?
Yeah. So as Carl's talking, feel free to ask any questions either in the chat or in the Q&A, and we will either answer them in the back channel or interrupt Carl at an appropriate time.
Let me share my screen here. Yeah. Okay, so let's start off by talking a little bit about why do I need a hex mesh, and then we'll go into using Coreform Cubit. I intend to spend most of my time actually in the code, and I'm using a piece of freshly compiled code, so I've run into a couple of issues. I will work around those issues. I'm not going to try and cover up the warts. There are warts. It's like any other software. So let's start off about that question first. I get to ask this question fairly often about, do I even need a hex mesh? And the answer is, it depends. It depends on your physics. People will ask me that question, well, do I need a hex mesh? And I will look at them and say, you're the domain expert in your field, you tell me. And that actually kind of takes a lot of people aback. They're like, well, I'm not the expert. I'm like, then you need to be. You need to become the expert. You need to know what's going on with your physics so that you understand it. It depends on your timeline. If you need an answer tomorrow, if you need an answer this afternoon, you may not have time for a hex mesh for all parts. It depends on how accurate you really need to be. If you're going to build something and throw an engineering safety factor of 5 on it, maybe not. Maybe you don't need a really accurate mesh for that. You don't need the accurate analysis. I was talking with Greg earlier today, and he said, yeah, if I've got $100,000 to build a stainless steel table, and I'm only going to put dinnerware on top of that table, go ahead and use PETs by all means. It doesn't matter. This little plot at the right here. So this blue line shows a very simple problem. Take a rectangular cantilever beam, so tie it at one end, and then start to twist it. And twist it until you reach plasticity, so things start to yield. This blue line represents a closed form solution for that problem. Simple problem, we can actually do a closed form solution. So this is a 2x2 quadratic hex mesh, and you can see that we're actually getting some pretty good correspondence with reality there. Down here at the bottom, just pure linear behavior is what happens with just a 2x2 TET mesh of that, which is really the worst possible thing you could do for this kind of a problem. But the behavior of TETs, linear or even with more, is by its nature linear. If you're doing thermal meshes, absolutely. If you're trying to do very accurate, high-end structural problems, especially when you're doing any kind of plasticity, you maybe need to look at hexes, or at the very least, you need to look at quadratic tetrahedral. Sandia has been advertising their new formulations for a quadratic tetrahedral that they think is doing very well. Those are the kinds of questions you need to be looking at and you need to consider. So what I'd like to do today is walk through using Coreform Cubit for a part that is non-trivial. This will take a little bit of effort, and we'll go ahead and use some of the tools in Cubit. One of the things that I will start is using what we call this breadcrumb navigation panel. This is a new look for Cubit. You can go into the options panel, turn on this breadcrumb trail, and it changes from the traditional big icons into this trail of breadcrumbs. We'll see that as I go through and use this. So let's go ahead and bring up Cubit. Okay. The first step in looking at any problem when you're trying to do a hex mesh is we have to start looking up at doing some manual cleanup. There's some features that typically we say, all right, I'm either going to ignore these features or I'm going to clean them up just to make my life easier. So that's where we start. So let's start by cleaning up some of these blend surfaces. So let's go into geometry, surface, modify. I'm going to select remove, and the pick widget icon's already highlighted up there. So I'm going to come over here and pick the surface. Now, one of the things I want to demonstrate here is when I pick that surface, there's an option here to select a similar surface. So it will look for surfaces that are the same area, perhaps the same overall general dimensions, and pick that as two similar surfaces. Now I'm going to go ahead and select blend chain. And it's going to take those two surfaces and select all the way around there for those blend chains. Rather than going click, 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 doing control click all the way around, I'll select the blend chain of those two items and hit apply and remove those blends. Removing those kinds of simple blends, especially when they're small, is one of those things that will make your life easier. Just as another example of that select, let's go ahead and select, I'm going to select the surface. I picked the wrong one, so I can hit the tab key and tab through and select different surfaces. Now I've picked that little hole, do a right click, and once again select similar surfaces. It's going to find the other hole with the same diameter. Hit apply, remove some small holes. I may say that's going to be filled up with a bolt anyway. That's just material. I don't really care about that. Those kinds of things are things that we clean up. Now, one of the new things that I wanted to show today, this model has a lot of features that we call tangencies. There are some really bad tangencies in this model. So I'm just going to pick a couple of these tangencies, and we're going to apply a new feature that we've been introduced. I'm going to go up here under geometry, pick vertices, modify the vertices, and blunt these tangencies. So I'm going to select these two vertices on this side, and I'm just going to let it use the defaults. If I preview this, what it does, it's adding some additional material around that tangent location. Now, once again, I'm making some approximations. If I need to know what my physics are, if this is a valid approximation to make. So I actually go in and modify my geometry, put these tangencies in there, and I'm going to do the same thing on the other side, but like I said, this is a new feature, and it actually is giving me some problems. So we'll preview it again. We'll say apply. And this time you'll notice it actually created these as a sheet body. There's still a volume underneath there. It did something funny. So I'm going to have to go in and say volume, modify, heal this volume, apply. I go back, and now I've just got the volumes, that sheet body went away. So that's just me working around an issue that we're still trying to resolve as we develop this new feature. But I wanted to show that because I think it's a kind of a, we get to the end and we'll compare what happens at these tangencies with what happens down here at these other tangencies and just look at what happens. So the first step then is this cleanup. We go through, we clean up our model, we get rid of some of those small features. In this case, we blunted some tangencies as well. The next step is we have to start thinking, how am I going to break this up into pieces that are actually meshable? Typically, we do that by going under volume and doing web cuts. Web cuts are the set of operations that we use to subdivide these volumes into things that are actually meshable. So let's go ahead and just say, okay, this is a planar surface right here. Let's cut everything off the top from that surface. Now I'm going to try this. Now you can keep going back and forth and selecting things. That's off the top. I'm going to select the bottom as well. So surface volume 1 is already selected. If I hit a middle mouse button here, You'll notice it took me from the volume pick widget down to the surface pick widget and lets me directly pick that surface, so I don't have to keep going back and forth. And I should be able to hit Alt-A. Didn't work on this one. I hit the apply, and that cuts that off. Now, if I look at my volumes here now, you'll notice I have one, the bottom, that little one down there at the bottom, 2, 3, 4 volumes that I've created with those two operations. Let's go ahead and look at, so those are plain operations. Let's go ahead and look at some other kinds of operations we can do web cut. Let's do, for example, a sheet extended from the surface. Let's cut through everything again, and let's pick that cylinder, extend that cylinder off and cut everything through there. So now I cut this volume off and I cut a piece of that off as well. Let's do a couple of other operations here. Let's look at now, instead of sheet extended from surface, maybe let's do a sweep surface. I find sweep surface to be a pretty powerful operation. Let's take this one and cut it through there. Now you notice that this has, I'm cutting perpendicular, I can do either inward or outward. Inward is actually the direction I want to go. Let's preview that and do an apply. And as we go through here, you'll notice I'm creating more and more volumes. Over here, I'm going to do some things partly just to kind of show you some operations. I could get away without them, but it gives me a little bit nicer mesh, and it just also demos some good capabilities. Let's go ahead and cut this volume. I went into transparent mode, you'll notice. And once again, I used my tab key. I selected this top surface up here, and then I did a tab. And as I tab through, it finds closed surfaces, so I can find this one. Now, this is actually a surface on a cylinder, so I can't do perpendicular on that. But my model just happens to be lined up nicely, so I can give that a positive Y vector. And I'm going to cut this up to this surface. I preview that. You see I've got this little dark blue section that happens in there. I'm going to apply, so now that's volume 8 that got created there. I'm also going to take the top of that surface once, oops, I want to cut through everything that it hits. And I'm going to pick the surface there, do a tab, and let's go here in the positive Z direction. Through all. There we go. And we're also going to cut through the negative Z direction. Now, once again, this one is not necessarily required, but it'll show some differences in actually doing some effort here and not doing it over there. Okay, now this volume over here, if we look right now, if I go into my power tools and come into my meshing power tool, select volume all, and analyze it. Okay, everything here is meshable except for this one. We haven't done anything with this yet. I hit this little refresh button over here to reset my colors. We're going to go back to command panels. So we still have to take care of this. So we can go back once again and sweep the surface through this volume. We can take that surface and preview, whoops, perpendicular. There we go. Z direction didn't make any sense there, left over from the last command. And apply that. Okay, now let me bring up my PowerPoint slide here for a moment. We've gone through the mesh cleanup. We've done some decomposition. We removed some sharp tangencies. Now, I wanted to just show in this area, you can see here, there's a little gap between the bottom of this flange and the cylindrical surface. If I actually go ahead and do a tri-mesh on that surface, you can actually see the tri-mesh is trying to capture those small features in there. So we want to make sure that we get rid of those so we just have a nice smooth mesh in there.
So while you're transitioning, Carl, just to comment, a lot of these techniques that you're showing are also available on coreform.com. We have dozens of tutorial videos. So if you find yourself kind of trying to remember what Carl did, feel free to reference those. But also, if anything's unclear as he goes through this, feel free to chat in on the Q&A. It's part of the value of a live webinar is the chance to stop the expert and understand really what's going on.
Absolutely. Go ahead and if you'll watch those chats, if someone has questions, please bring them up. Now, the other thing that I do want to point out, I've taught dozens and dozens of Cubit courses over the years. And before that, I was the in-house Patran expert back in the day, my first job. And one of the things that I know is from doing courses and watching these things, I don't expect you to remember exactly how to do it. What I do hope is you remember that it can be done. And once you remember that it can be done, then there are resources like those that Matt was just talking about that allow you to actually go figure out, okay, how do I do that thing? I know that can be done. How do I do that? So we've cleaned up some manual features. We've done some decomposition. Let's go back and check our meshability. I bet this thing is still not totally meshable. Let's select all again. Let's analyze. It's not. Now I know one of the reasons why this one is. I'm not sure why this region is not meshable yet. Should be. We'll play with that one in a little bit. It's the value of a live demo. You're saying, oh, that was a surprise. Okay. This volume has what we call a periodic surface in it. So that periodic surface we'll need to take care of. But we're going to go ahead and go back to our command panel, go into volume, imprint and merge is our next step. Now, remember I told you we've got this little small gap in there. We don't want to do just a regular imprint. That will just leave that small gap. So we're going to go ahead and do a tolerant imprint. Now, one of the things I want to comment on tolerant imprint, we're going to say, oh, well, I want to do this on everything. Just take some caution with tolerant imprint because sometimes it does more than you want it to do. I'm going to merge. I'm going to set the tolerance to 5 here. Let me look at this first. That volume concerns me why that didn't come out being meshable, because it should be. All right. There's nothing there right now. I'm just going to use the command line because I know the command line really well. If you watched Trevor's demo last time, he says he does everything from the journal file. Let's go ahead and apply this. Okay, we're going to look through and it says, all right, there are 2 pairs of curves without a surface that were not right. And that's the one that I was having problems with. Okay, once again, like I said, this is a real live demo. Don't know why that didn't work. It should have worked. Let's unmerge everything. Oops. See, that's gonna regularize. Let's unmerge all first.
Would it help to regularize the volume?
Well, that's what we're gonna do.
That was the suggestion from Trevor.
Yep, we'll go ahead and regularize everything, which is essentially what this unimprint volume does. It's going to do a regularized volume all. Okay. Let's try doing the imprint and merge one more time. And as I was running through this today, this is something that I ran into again. Okay, that's correct. That's what I'm looking for. And I've got my, there we go. Well, let's go look at our power tool. Oh,
So how, Carl, for those that don't know, what does regularize mean in this context? Why was that the secret bullet?
so essentially what happened was, I believe from before, there was some kind of an imprint, and an imprint is just the one surface mapped onto another surface. So for example, if we look at this surface here, if we just draw this volume, all of these curves come from the adjacent surfaces, the volumes on those, the surface on those volumes that are adjacent, and they get mapped onto this adjacent surface. And if we look at the bottom, they're not there, they're just in this area.
Right.
Now, and in fact, if I go ahead and do a draw surface all with is merge. And one of these days we will have a full webinar talking about what kinds of things can you do with the command line. I draw all of these surfaces, and this shows me all of the surfaces where the volumes are connected. Obviously, if I'm doing contact, this is not what I want. But if I'm just trying to create a mesh with a single part, these are all the pieces that are actually merged together. Now, what regularize does, regularize would take this volume and remove all these curves, extra curves. It would keep all of the exterior, but everything that's internal here, where I could recognize, oh, this is a plane surface. And
Got it.
yes, go ahead.
Okay, yeah, so just removes those interior imprinted curves.
Right.
I've often referred to it as it removes redundant features. So extra vertices that aren't required to define an arc, extra vertices on a straight edge that aren't the bounds of it. Anything that's extraneous, doesn't define real topology on that volume, it removes.
Okay, thanks, Carl. You can proceed. Thank you.
No, that's really good. Thank you, Greg. That's why we do this webinar.
And it is a good point. There was a QA that I answered too, but when we do web cuts, unlike other software that do partitions, when we do a web cut, it completely disconnects volumes from each other. So they don't communicate, they no longer communicate. So if you were to mesh each one of them individually, they wouldn't communicate like their mesh edges or mesh nodes to create a conforming mesh. So they are completely separate. And so the process of what Carl mentioned of imprinting and then merging those surfaces together is what allows the mesher to communicate the mesh across volumes. And sometimes you want that, but like Carl said, with contact, you wouldn't want those to be connected.
Right. So you do want control of those kinds of things. Okay. Now I'm willing to bet if we were to go back to our power tools, let's look at this again. Select all and analyze. Yeah. All right. So this one is now meshable. This volume still is not. You'll come across some of these kinds of volumes that you think, why isn't this meshable? It looks like what we're looking for to create meshability is essentially if I can define either a many-to-one mapping. So for example, this volume, I have many surfaces up on the top here, and I'm mapping to one surface. That's something that's easily meshable. And on this volume, you'd think, well, I have one surface on the front here. Surface. I have one surface here on the front. I have one surface there on the back. How come that thing's not meshable? These kinds of cylindrical, topologically cylindrical surfaces are what are called periodic surfaces. And sometimes we need to go ahead and split those periodic surfaces. We're going to pick this volume and split the periodic surface. You can see now it put in an extra edge on the interiors of those volumes. If we come back to our power tools now, and let's just pick this volume and analyze it. Huh. The magic was supposed to work. The joys of a live demo. Okay, let's actually, we'll reset that. We'll see what happens. We may have to go back and be explicit on this one, or there may be, due to the blunt tangency, something that's going on in this area. So we may have to actually debug that live, but we're almost done, so we have time. So let's go into our mesh, and I'm going to just go ahead and pick an approximate size for this on all my volumes. Get a volume of 0.15. And apply that size. I'm just going to go ahead and try to mesh it and see what happens. I bet this volume doesn't actually mesh. It didn't. So we may have to go through and actually be explicit. And sometimes that happens, where there are cases where you actually have to say, okay, I don't know why the automatic schemes didn't work, and so it couldn't automatically calculate it. Sometimes I have to just go ahead and specify what the source and targets are. So we're going to pick this volume and select that as a source surface. That is a source surface. The end of the, oops, we can go to the next one. There we go. Let's apply that scheme. And it says that, okay, surface 137 does not admit a type of submap. So this is where the new kind of thing that I'm trying to show you isn't being helpful. Let's locate surface 137. Okay, I'm willing to bet if we were to go look at this, let's go into prepare my geometry and remove small features. And there is a small curve. Okay. That's why it doesn't like it. There is a very small curve that was created by that blunt tangency.
So Carl, how did you find that again in slow motion?
Okay, in slow motion.
That was a good trick.
Okay, let's go back here. I was in my command panel. I went to my power tools. No, actually, I went into item. And let's go till item undone so we can get back. And I went to remove small features. And I said, okay, let's analyze, let's detect small features. And there is a small surface there, surface 137, and a small curve. So, but that surface area is 0. So it's really something funny. So Trevor, this is something to report to Corey. And what I did was a fly-in. That didn't really do me very good because it's from a funny angle. But if I point to this and then right-click, zoom to that, I get a very small curve there. Now, I may have to delete all of my mesh. I don't know. This may not have meshed at all, so it might be good. So here I have some different options. So I can collapse to the vertex. I think I want, let's see if that will actually work. Collapse. Okay. Now if I look at my curve here, now this curve is one longer curve. Let's run our detect small features one more time. And now it says that there are 0 small curves. Okay. I can click on my triad just to restore my default view. Let's try selecting this again and just see if we can say mesh and see what happens. Okay, it still didn't like it. Okay, so there's still a surface 137 there that we probably have to find and delete. So we have to look at that. There is a really small surface that got created by that blunt tangency in this area. Okay. Like I said, these are the joys of doing a really live demo. And I've been through this multiple times and I'm still seeing things that I hadn't seen before. So I'm going to come to this surface. I'm going to pick surface modify. And I'm actually going to composite that surface out. I'm going to pick this surface 137. I don't even know if I can pick it. It's so small. There we go. There's surface 137. And I think I'm going to attach that to this other surface and create a composite. And this is something that I'd actually thought about doing, was demoing composites. A composite is not it's an overlay of what we call virtual geometry on top of the real geometry. That overlay allows me to go ahead and take that surface 137 and just composite it in, make it part of this underlying surface now 260. Let's see if I can mesh that one piece. Okay, that will mesh now. Before that didn't mesh. Let's try the whole volume again. Let's say, select the volume, not just the surface. And let's try meshing that. There we go. So this blunt tangency operation, which is a new feature that I'm just trying to demo, it created a small surface in there. We had to get rid of that small surface. Now, one of the things I wanted to talk about.
Hey, Carl.
Is what the effect, yes, go ahead.
Just while you're on it, someone asked, how is a composite different from a tweak?
A tweak modifies real geometry. So it modifies the ACES geometry. So it's an operation on a BREP solid. Tweak overlay, or excuse me, composite overlays that BREP solid with a piece of, we'll call it fake geometry. It's just, so it's based on the underlying facets. And if I create some of that virtual geometry, there are some operations that I cannot do on the BREP geometry after creating virtual geometry. Okay, so now let's take a look at this. Now you'll notice that I didn't do anything to break this up explicitly. So this put a paved mesh around here. Whereas over on the other side, where I had gone through to some effort to break this up, it automatically put a mapped surface here. So that's one of the differences. And that's just one of the things I wanted to show. Now let's go ahead and look at some mesh quality. And let's look at all. And we'll go ahead and use a scaled Jacobian. Now, up here in this area where I fixed that blunt tangency, so if I go ahead and select a hex, and that one's probably one of the brightest colored ones, and show the quality on that. So that element has a quality of about 0.654. So up in this area on a scale of 0 to 1. Anything over roughly 0.3, now just as kind of a rule of thumb, is pretty darn good. But if we come over here and look at these areas where we didn't do anything about the sharp tangencies, you'll notice in this area, for example, if I show its quality, okay, the quality is 0.01. In all of these areas where I've got these sharp tangencies, I have a much poorer quality element mesh. But the trade-off may be, I may have perhaps like a score along there, depending on my physics. That may be important because I don't have a pure cylindrical surface along there. Trade-offs. Creating a hex mesh is all about making trade-offs. And deciding what those trade-offs are and how to make those trade-offs is really part of the art of the finite element analysis. I'm going to go ahead and you may not have known you could do this. You can grab that bar, move it around. I call these features for creating journal articles. That's why we add some of those kinds of things in. But creating a high quality hex mesh really is about trade-offs, understanding your physics, and knowing what to do. We've gotten into a few extra things that I hadn't anticipated because we ran into some issues with some new features. Greg, you want to talk a little bit about the mesh quality? Greg added some.
So one of the questions that we often are asked is, there's a lot of different quality metrics, and how do I know which metric to use and what's the best metric to use? And you're probably going to be tired of this, but the answer is that it depends on your specific application. That for some cases like CFD, your quality might be how good are my elements, my boundary layer, and are they aligned with my flow? But a good general purpose, or probably one of the best general purpose metrics, is called the scaled Jacobian. And this is just here, I'm just showing an example of what scaled Jacobian is. You can think of it as a metric of the quality of the mapping from the parametric space of an element into its actual configuration in your mesh. And so it's how much is my element being distorted at a given spot. Now, in this case, we have a quadrilateral, and I'm plotting on the left the scaled Jacobian values across the element. And of course, when you see the results in Cubit, you only see like a single value per element. It will be handed out. And I just checked with Carl, and I believe that the way that we do scaled Jacobian in Cubit is we evaluate each node of the element to see what the scaled Jacobian values are at the nodes, and then we print out either the max or the minimum of those values. But effectively, what you can see on the right is that, which again is plotting, we're actually taking an element from its parametric configuration and we're deforming it. And you can see like these lines of equal values of the parametric space. Eventually, this element inverts. And at a point of inversion, you hear about like element inversion a lot of times in your finite element codes if you have a lot of deformation. That's where effectively there's no longer a one-to-one mapping between the parametric space and now the deformed configuration, and your solver can no longer proceed. And that will occur at a scaled Jacobian of essentially 0 or infinity, depending on how you look at it. But so scaled Jacobian is the metric I recommend the most. And the reason why I say scaled Jacobian is that scaled Jacobian takes the size of your element into consideration. And so if you have, say, one element whose dimensions are 100 by 100 by 100, and another element, and they can both be cubes, and another element that's like its dimensions are 0.01 by 0.01 by 0.01, the Jacobian for both of those elements will be different. One will say that its volume has gotten bigger, and then one will say its volume has gotten smaller. But typically, just the value of the Jacobian itself doesn't really have a huge impact on the quality of your results, as much as the scale Jacobian does, which really captures the amount of distortion, more so than just whether or not the element's gotten bigger or smaller. So I recommend scaled Jacobian as a good quality metric to use. I think if you go to the next slide, just as a kind of a fun, again, it's really a metric of the mapping. And so, of course, we talk about mappings. Why not show a map of, of the world? And so, just to try to think about, right, we're trying to put ourselves in the place of the computer. But if you were to imagine, if you give someone a map, like on the left, and you ask someone to point which direction, if I'm starting in maybe in Paris, which direction is north, right? Or which direction is east or west? And it's easy on the configuration on the left to tell which direction is which. And so the same way, computers, it's easy for it to tell what, if I am looking at a different point in my element, how does this relate to its neighbors? If I look at the map on the right, if you were to give someone said this map and say, here's Paris, and you didn't show like these little ISO curves that kind of show you which direction's north and which ones are east or west, and now you asked them to tell you which direction was north and south and east and west, that would be harder for someone to pick out exactly which direction is north and south. And so in the same way, the larger our deformations of our elements are, the more the computer has to think about the solution, and the more the solution can potentially degrade. And so if that's a good mental model for what scaled Jacobian is and why it matters, and why it's a good general purpose metric, hopefully that's helpful. But then what I will say is that, in my opinion, the best metric for how good is my mesh is how good are my results. And at the end of the day, that's really all that matters, right? You can look at all these different metrics, but if you have results that don't make sense, then your mesh isn't very good. And so really the best metric is how good are my solution results. And so you still have to consider verification and validation in your simulation processes. It's not just enough to say I have a good quality mesh based on these metrics. You still have to do V and V.
Very good. Thank you, Greg. Just kind of following up with Greg's comment on that. Once again, I said at the beginning, people ask me, well, what kind of mesh do I need? And I tell them you have to be the domain expert. You have to be able to look at your results and see if they make sense. You need to have enough engineering background to know, no, that doesn't make any sense at all. I don't see how that could happen. Go back to your, initial sophomore year kinds of classes in the university where you're looking at some of these problems and say, how does that apply? Does this make any sense? We can give you, some guidelines, we can give you rules of thumb, but in the end, you are the engineer. We do have support. Glad you were able to come and participate in our webinar today. We can go to www.coreform.com, go to the forum. We're actually getting users that are answering other user questions now, which is really helpful. There are Qubit 100 and Qubit 200 courses, webinars like this one that we'll continue to do. There's also the YouTube channel out there that gives us a number of examples, problems that are worked through. And we'll continue to add to these things, and grateful that you're able to participate with us today. We have an additional webinar coming up, as Matt suggested earlier, Introduction to Coreform. There are other webinars on the schedule that you can find online at coreform.com/support/webinars. Thank you for your attendance today. We appreciate your time. Hope that it was useful. Thank you very much.
Thank you so much, Carl. Appreciate that. I think we've just got a couple minutes left. If anyone has any other questions, we can stay on the line and answer them.
Carl, there's some questions about so mesh refinement, mesh scaling. So I've done a couple answers on it so far, but maybe to just kind of address this, and I know that you probably got a little more experience here than I do. Am I remembering that there are some parallel mesh scaling capabilities to do?
Yes, there are. There's a and those parallel capabilities are enabled, I think, on Linux. I'm not sure that they're enabled in Windows. So if we go into mesh and we go into volume refine, this mesh scaling is a scaling option that will create much larger meshes. Know that's one method of doing that.
There's also like general refinement, I think, is another option.
Right. There's some, and
Yeah,
the general refinement is a base refinement. I think the mesh scaling is the one that would get to many elements.
Yeah, and Trevor's indicating that's a serial process.
That is a serial process. Okay, so this one's not the parallel version. Okay.
Hey, Carl.
So, yes.
Can you, a question was asked. Someone uses a lot of meshing software. So what are the main advantages of Cubit over something like Hypermesh or ISOM or any of those others?
I'm not going to downplay the competitors. They're good. ISOM for certain applications is really good. For Hypermesh has a very nice user interface. One of the primary advantages that I find actually of Cubit, and one of the things that is really, really helpful, is this ability to, I can go into the journal file and do an import and pick my, let's say I go to the history tab, and I can get all of my commands, and I can take a session and go through and actually script that session out. So I could replay this without any problems. Cubit scriptability, I think, is unparalleled. When you go to the Python interface and start actually programming to do things in your mesh world using Python, I don't think there are any other tools out there that match that particular capability. And frankly, the ability to script things and redo them and to modify those scripts, I think that's one of the places where Cubit is really most powerful.
Yeah, and we've got some webinars that we'll plan in the future. Hopefully not too far in the future to show and demonstrate how to use the Python API to automate Cubit. And one of the things that's really powerful is that with the Cubit API, you can do things like query the underlying ASYS geometry kernel to do things like compute like a normal at a given point on a CAD surface and do operations with those, right? And you can find the distance between, say, a point in space and a given surface, and whether that should be on part of like the real surface or if that surface was extended. There's a lot of different functionalities there, so like one of the webinars that we're going to show is actually show how to create CAD models of grain structures and to do things like iterate and optimize those grain structures with like Lloyd's algorithm to give out equiaxed grain structures. So I really do think that the most powerful feature of Cubit, and I agree with Carl, the most powerful feature of Cubit is the Python API. It allows you to build your own workflows. It's really powerful.
So someone asked which version of Coreform Trellis is used here. So this is version 2020.2, and we will be releasing a point release within the next couple of weeks that will include all of the features that I've demoed here today.
Yeah, a comment, Carl. They're a company, they use SolidWorks. They import the CAD from SolidWorks into Cubit, and it's really challenging because SolidWorks adds lots and lots of fillets. It's a kind of a dirty model. I'd like possibly a seminar that addressed just that subject. We've seen that recently, haven't we? Yeah.
Right. So SolidWorks is actually, it's better than AutoCAD. So that if they could give us some models that we could play with, that would be really good.
Also, we do have a SolidWorks importer that you can purchase separately. So it'll take your SolidWorks model, import it into Cubit, and will handle it very nicely. Maybe not introduce so many small features and things.
Okay, and someone also asked about the cut command. So nothing ever disappears in Cubit. It typically goes behind what we call a set developer flag. So if you were to do a set developer on, you can get to that cut command. I believe it still exists. Since there is additional work that is being done at Sandia right now on some of those kinds of things where they're applying some machine learning, some of those kinds of tools. I need to go, I have actually not seen a lot of those demos, but that's some additional work that is being done behind the scenes.
It's also a good question on mesh-based geometries. And so one of the things with mesh-based geometry, so it's actually a different geometry kernel in Cubit. It was hand-rolled or hand-developed by Sandia. I guess one of the things I'll say is that it is not as robust. That kernel, or you can think of it like kernel as like a geometry engine. That engine is not as powerful and robust as the ACES kernel, which is licensed from Dassault Systems Spatial Corporation. And so not all operations are supported with facet-based geometry. You can sometimes, some of the features are just hidden behind developer commands, but it kind of does reflect that when you're working with facet-based geometry that there's just not as much robustness there. So my recommendation is one of two things is, first of all, to try not to work with mesh-based geometries in the first place if you can. So sometimes you might have your customers giving you a CAD model that they might have a CAD model like in Creo or SolidWorks, and they're giving you an STL file of it. And that STL file can only be processed in mesh-based geometry. So my suggestion in that case would be to request them to give you either the native CAD geometry and then use one of our CAD translators, or to export out like a step file or an aces.sat file so that you can actually operate on the actual CAD. Sometimes, however, that's not possible. I recognize that, especially with like topology optimization, or say that you're taking a mesh from a previous simulation and you're trying to operate on it. And so my suggestion there would be to use an STL-centric CAD software, so like MeshLab or similar software to that, to do any of your Boolean operations that you need to do beforehand. That those typically are more robust. We're trying to get more robust in mesh-based geometry, but that's and we're looking at maybe alternatives, but we just don't have the best solutions for mesh-based geometries today.
All right, so we've about wrapped up our hour. There's a couple other questions that have come in. Do we have a brief response for any of these, and then we can wrap up?
Yeah. So this one about local mesh refinement. So we're actually developing sizing sources that will allow you for, say, TET meshes to define regions of local refinement. But also that's a good opportunity or good area to use the Python API to define where to put small elements and because you can query the geometry and stuff like that. So that's another area that might actually be the topic of a future Python webinar.
Okay, again, thank you all so much for spending some time with us today. This webinar recording will be posted, and we look forward to engaging with you more in future webinars and also at our forum at coreform.com. Have a great day.